Okay, we just finished up some optimization problems, and now we're going to look at related rates problems. Our first example, we have a car and a bike that are traveling along perpendicular roads. The car is traveling at 20 miles per hour, and a motorcycle is traveling at 180 miles per hour. At 3 o'clock, when the bike is at the intersection, so the bike is starting here at 3 o'clock. The car is 195 miles away and moving towards the intersection. So this is the intersection point right here. It wants to know what is the rate in miles per hour that the distance between them is changing at 8 o'clock. So this is going to be the distance between them at 8 o'clock. So at 8 o'clock, the car has moved to this position and the motorcycle has moved to this position. So at 3 o'clock, the motorcycle's here, and during 5 hours, the motorcycle ends up over here at 8 o'clock. The car starts here at 3 o'clock and travels here over a 5-hour period and ends here at 8 o'clock. So at 8 o'clock, the car is here and the motorcycle is here. So the picture that we're looking at is at 8 o'clock. And at 8 o'clock, they want to know what rate is the distance between them changing. So z is the distance between them. The rate that the distance between them changes is going to be z prime. So what we're looking for is we're looking for z prime. That's going to be our final answer, z prime. Now, because we do have a right triangle here, we can create the equation x squared plus y squared is equal to z squared. We know we're looking for z prime, so we can do the derivative and we'll have a z prime. Now, for all of these problems, we're going to do the derivative with respect to time. And you'll notice none of these are a t. So every time we do the derivative of those pieces, we're going to have the chain rule. So when we do the derivative of this first piece, we're going to get 2x, but then we're going to get x prime. I'm going to write that as dx dt, but that's the same thing as x prime. Same thing for the derivative of y squared. It's going to be 2y and then y prime. Same thing for the z squared. It's going to be 2z and then z prime. Now I'm trying to solve for dz dt. So I can just divide everything by 2z. My final answer will be, now I want you to notice that you can either write it as dx dt or you can write it as x prime. Same thing with the dy dt. You can also write it as y prime, or dz dt. You can also write it as z prime. But now that we've solved for z prime, remember z prime was our final answer, we just need to figure out what all of these pieces are. We need x and x prime, we need y, y prime, and we need z. Now the first thing we can figure out is the x, the y, and the z at 8 o'clock. Remember, this is the picture at 8 o'clock. The motorcycle was here at 3 o'clock, but then traveled to here, and now at 8 o'clock, that's where the motorcycle's at. The car started up here at 3 o'clock, it traveled, and now it's here at 8 o'clock. So that triangle represents our picture at 8 o'clock. Now, if the motorcycle was here at 3 o'clock, and it's now here at 8 o'clock, that means it traveled for 5 hours. I want you to notice that the motorcycle is traveling at 180 miles per hour. So we want to do 180 miles per hour times 5 hours. Okay, I think you notice that the hours are going to cancel, and our final answer will be 900 miles. So the distance from here to here is 900 miles. So we can plug in a 900 for the x. Now the car was here at 3 o'clock, and the car is here at 8 o'clock. And the car was only traveling at a rate of 20 miles per hour. But it was also 5 hours. Again, we can cancel the hours, and we're left with 100 miles. But be careful, 100 miles is the distance from here to here. That's 100 miles. The total distance to the intersection was supposed to be 195 miles. So that means y is going to be 95 miles. We can plug that in right now. And because we know x and we know y, we can use this equation to find z. Z is going to be the square root of 900 squared plus 95 squared. And that comes out to 905. We can plug that in right now. Now, because this distance here is x, then x prime is going to be the rate of change of x. So that'll be how fast the motorcycle is going. And that's going to be 180. We can plug that in for x prime. It's going to be 180. Now, this side of the triangle is y, and this side of the triangle is decreasing at a rate of 20 miles per hour. Because it's decreasing, we're going to use negative for the rate. Notice this side was increasing, so its derivative will be positive. And this side is decreasing, so its derivative will be negative. So y prime is going to be negative 20. We can plug that in. And that'll be our final answer. You can leave it like that if it's a free response question. Or if you want to type it in a calculator, you would get 176.906. Don't forget the units. Remember, this is z prime. So it's going to have the same units as x prime and y prime, and so the units will be miles per hour. Okay, there's a couple of things I wanted to point out about this problem before we move on to the next one, and that is that this is x here. So if that's x, then the rate that x changes is going to be x prime. When you think of rate, you can kind of think of speed. It's kind of like how fast you're going. That's an example. Miles per hour would be a good example. But if that's x, then x prime would be the rate. They do give you the rate at 180 miles per hour, but since that side of the triangle is increasing, because the motorcycle is going to the right, then its derivative would be positive. Similarly, for this side of the triangle, we're calling that y, the rate that y changes is going to be y prime. They give that amount, it's 20 miles per hour. But we put negative in front of that because that side of the triangle is decreasing. When something is decreasing, its derivative is negative. So that's a really important concept that we need to think about. Same thing with z. If that side of the triangle is z, then the rate that z changes is going to be z prime. And that's what they were asking for on this question, was z prime. Remember, all derivatives in this section are going to be done with d dt. So when you have a letter that's not t, you have to do the chain rule. And so for each piece, you're going to get an extra prime piece. Okay, this one's a bit of a geometry kind of question, and we'll have to do a derivative, but the derivative will be really easy. So we have a 16-foot tall giraffe. The height of our giraffe is going to be 16 feet, so I'm marking it in the diagram below. And it also says that the light pole is 40 feet tall, so this light pole is 40 feet tall. Now I've decided to call this distance here an x. It doesn't matter if you call it x or y, I'm calling it x. And because the rate of the giraffe is 50 feet per second, and that means that x is going to change at a rate of 50 feet per second. So we'll say that x prime is 50 feet per second. Now the question is, how fast is the length of the shadow changing? Now the shadow is here in red, we're calling that y, and the rate that that changes is going to be called y prime. So our answer is going to be y prime. Now in order to find y prime, we're going to have to create some equation, but we do have similar triangles. The reason we have similar triangles is because there's a right angle here and a right angle here, and they both share this angle over here. So you can see that they are similar because of angle, 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 right? If two angles are congruent, then that third one is also going to be congruent. So because these triangles are similar, we know that the ratio of their sides is going to be equal. So we can use this little triangle here, and we can say that 16 over y is equal to, and then we'll use the big triangle, and we'll say 40 over x plus y. If you remember from geometry, if you have a fraction that's equal to a fraction, one of the ways you can solve it is by what we call like cross multiplying. Y times 40 is equal to 16 times x plus y. Remember, we're trying to solve for y, so let's subtract 16y from both sides. And then we divide both sides by 24. And because 16 is 8 times 2, and 24 is 8 times 3, we can cancel the 8's, and this becomes 2 over 3x. Now, we haven't actually done any calculus yet, but we did come up with an equation that relates y with x. Remember, we're looking for y prime, so let's just do the derivative. Remember, we're doing this kind of derivative because we want to see how this picture is changing as time changes. So we're doing the derivative with respect to time. So the derivative of y is just going to be 1, but then we're going to get y prime. The derivative of 2/3 x is just 2/3, but then we're going to get x prime. If you remember from the beginning, this is x, and the rate that x changes was given at 50 feet per second. So we can trade that right now. If we plug in 50 feet per second, our final answer is that the length of the shadow is changing at a rate of 100 feet per second. Now, if you go onto YouTube, there is something called the shadow question, and it's basically what we just did, but sometimes they'll ask an additional question. They'll say, how fast is the tip of the shadow moving? Now, if you want to know how fast the tip of the shadow is moving, you have to add the speed of the giraffe. So the shadow itself is increasing at this rate, but because the giraffe is running, that means the tip of the shadow would be increasing at the rate of the shadow plus the rate of the giraffe. So the length of the shadow is changing at a rate of 100 over 3 feet per second, but the tip of the shadow is increasing at a rate of 50 plus 100 over 3 feet per second. So those are two different questions, but whenever you look up the shadow question, those are the kinds of questions that they can ask. Okay, here it says that the wine is spilled from a barrel and it's spreading in a circle whose circumference is increasing at this rate. So the c is the circumference. The c prime is the rate that the circumference is increasing. So we can fill that in right now. C prime is going to be 30 feet per second. It says how fast is the area of the spill increasing? So A is the area. The rate that it's increasing is A prime. So our answer is going to be A prime. And we want to find A prime when the circumference is 90 feet. Remember the rule for circumference? Again, we want this to equal 90 feet. So the circumference, which is basically just the perimeter of the circle, that is going to be constantly increasing. We want to stop at the moment when the circumference is equal to 90 feet. Since we know we're looking for A prime, let's take the area of the circle and we'll do the derivative, and that will give us A prime. The derivative of A is 1, but we're doing this kind of derivative, and that's not a t, so we're going to have to do the chain rule. And that'll give us dA dt, which is A prime. Remember, this is just a constant, so when we do the derivative, we're really just doing the derivative of r squared. That'll give us a 2r, but again, we need r prime. I'm going to write dr dt. This constant that was in front of it, we just bring it down. And so this is our final answer, but you notice we got to figure out what is the r, and we got to plug in the dr dt. Now to find the r, we can solve this equation for r, or if you're really tricky, you'll see that there's a 2 pi r here and a 2 pi r here, so we can just trade the 90 feet for the 2 pi r. Now we still need dr dt, which is r prime. If you remember from the beginning, they did tell us what c prime is, and since we have c, let's just do the derivative, and we'll be able to trade c prime for 30 feet per second. That may help us find the dr dt, which is our r prime. So to do the derivative of this, we're going to do the derivative of c, which is going to be 1, and then dc dt. Remember, the 2 pi is just a constant, so when we do the derivative, we're really just doing the derivative of r, and that'll be 1, and then r prime. Again, we know what dc dt is. That was given to us in the beginning. It's 30 feet per second. So we can plug in 30 feet per second, and since we're solving for dr dt, we just need to divide both sides by 2 pi and we'll be done. So we can trade dr dt for 15 over pi feet per second. Now I want you to notice that there's a foot here and there's a foot here, so we're going to end up with feet squared. Now it does make sense to have square feet because this is an area, so that the rate that the area changes should be square feet per second. Now 90 times 15 is 135, so our final answer is that the area of the spill is increasing at a rate of 135 over pi square feet per second when the circumference of the circle is 90 feet. Okay, for this example, it says in the figure shown, the Wizard of Oz is lifting off in a hot air balloon. He's going straight up. You can see that happening over here on the right side. It says 500 yards away, the Wicked Witch of the West is watching. So that's going to be a constant distance. At the moment, her elevation angle is pi over 4. So we want to stop when this angle is equal to pi over 4. Now, as the air balloon lifts off, that angle is constantly changing. But we want to stop at the moment when that angle is pi over 4. And when theta is pi over 4, the balloon is rising at a rate of 80 feet per second. So if the right side of that triangle is y, then when theta is pi over 4, we would say that y is changing at a rate of 80 feet per minute. So that means y prime would be 80 feet per minute. So we're going to stop when those two things are happening, but keep in mind the angle theta is constantly increasing, and so is the side y. The side y is constantly increasing as well. There's only one thing that's not changing, and that's the bottom of the triangle. That distance is not changing. Now this is the only problem that I've seen so far that we've done where they mix up yards and they mix up feet. So we got to be very careful. We need to change them all to yards, or we need to change everything to feet. So what I'm going to do is I'm just going to change everything to feet. I know that for this angle here, we can come up with the ratio that tangent of that angle is going to be opposite over adjacent. So that would equal y over 500 yards. You can see that equation here. And we're going to trade 500 yards for 1,500 feet because 1 yard is going to equal 3 feet. So if we plug in 3 feet right here, it'd be 500 times 3 feet, which is 1,500 feet. Now the question is, at what rate in radians per minute is the angle of elevation changing at that moment? So theta is the angle of elevation, but theta prime would be the rate that that angle was changing at that moment. So we're looking for theta prime. Okay, so we have this equation. We can do the derivative. Again, we're doing d dt. Notice none of these things are t, so we're going to have to do the chain rule each time. Okay, we're going to start by doing the derivative of both sides. The derivative of tangent is secant squared, but it's a theta, not a t, so we need to do the derivative of theta, and that would give us theta prime. You can write it as d theta dt, or you can write it as theta prime. When we do the derivative of the right side, the bottom is just a constant, so really we're just doing the derivative of y, and that would be y prime. You can either write y prime, or you can write dy dt. Now I do need to solve for d theta dt, so I'm going to start by getting rid of secant squared of theta. I can rewrite secant squared as 1 over cosine squared. And if I multiply both sides by cosine squared, then I'm just left with d theta dt on the left side. Remember, we're trying to find theta prime when theta is pi over 4 and when y prime is 80 feet per minute. So we can plug those two things in. So we'll trade y prime for 80 feet per minute, and our angle theta is just going to be pi over 4. Cosine of pi over 4 is going to be root 2 over 2, and if you square that, you get 2 over 4, which is 1/2. You can multiply the 1/2 times the 80, that'll give you a 40. You can cancel the feet with the feet. And remember, this is an angle, so we have two ways of measuring angles, either degrees or radians. There's no degrees here, so this is going to be radians per minute. And we can simplify this a little bit. You can cancel the zeros, right? That's like 10 divided by 10. And you can divide both numbers by 2. You get 2 over 75. Okay, so our final answer is that theta prime is equal to 2 over 75 radians per minute at that moment. One of the most important things that I want to point out in this problem is that the angle of elevation theta was changing, so we did not plug in the pi over 4. We left it as theta. Also, the y was changing because the hot air balloon was still rising, so we did not plug anything in for y. We just left it as the letter y. There was one amount that was constant, the 500 yards, that was constant, so we were allowed to plug it in right away. We did not have to call that side of the triangle x. We could just put 500 yards, or 1,500 feet. So if something is constant, you can plug it in before you do the derivative, but if something is changing, you have to leave it as a letter, and then you do the derivative, and after doing the derivative, then you can plug in the specific stuff. So our angle was changing, but we wanted to stop at the moment when our angle was pi over 4. The y was changing, so we couldn't plug it in right away. But the bottom of the triangle was constant. It was a 500 yards, and it was not changing. So we're allowed to plug that in before you do the derivative, and it will make your derivative much easier. Instead of having to do a quotient rule, it was just a simple power rule.